When we think about dimensionality reduction, we might be wondering, when should we be applying it? One important reason is because of big data. Data nowadays comes in the form of many instances and may have actually thousands or millions of dimensions. For example, images have literally several million pixels coming in. Natural language text also might have the dimensionality of the vocabulary, and stock market time series data is quite voluminous. We'd like to know whether we can describe these sources of information more succinctly. For example, it would be easier to fit a model to it if we had fewer parameters and fewer input dimensions. Just as we did with the NUS data, we summarized that as just looking at intensity and horizontal symmetry. It's also easier sometimes to visualize because as humans, it's very hard for us to imagine things past 4 dimensions. So when we're trying to understand the data visually, it may help to project it down into a smaller number of dimensions. We also might be trying to discover the intrinsic dimensionality of the data. In other words, the data itself might have a lot of redundancies or correlations, and removing them would help us discover a notion of how many independent dimensions of the data is in the data set. So let's take a look at an example of stock market data. Even though we might have many takers of data for individual stocks, there is some type of inherent structure in mind. For example, a certain basket of equities might change in a similar way. For example, all the stocks that are related to transshipment are going to be affected by the same global events in the same way. And it's probably easier for us to measure the difference between a transshipment stock and its peers rather than to look at each of them individually. The same goes for regional stocks. A regional stock might be characterized by a regional average, with small deltas measuring the fluctuations between these individual stocks. For these reasons, we might capture an average for either a region or a particular domain of stocks and use less information to get a good approximation. This capitalizes on the structure inherent within the data. It would help improve our models because we have a stronger signal-to-noise ratio for our inputs. So what we'd like to do is do a projection into a lower dimensional space. Unlike what we can do with feature selection, where we pick a subset of features to represent the whole, we can construct new features that are combinations of the existing features. We're going to do this in the unsupervised setting by just looking at the data matrix X and ignoring the Y values. Let's take a look at this case of X values that have two components, an X1 and an X2, illustrated here in the XY plane. All of the blue points here have some correlation where X1 increases and X2 also increases. What we'd like to do is find some mapping, phi, which allows us to map our coordinates x1 and x2 and represent them using a single number, z1, to represent the point. This is going to require that phi take a linear transformation, which is going to create a single vector v, which has coordinates in the normal x1 and x2 space, in such a way that it captures the information of the points as succinctly as possible, using only one coordinate. That means when we have an input point xj in the higher two-dimensional space, we're going to pass it through the transformation to get a single number z. We're going to take the z coefficient times it by the v vector to get out a new representation of the point in the x1, x2 space. As you can see here, what we'll end up getting is a representation just along the v vector itself times by a coefficient, where we recover a point which is the closest point on v to the original x. We're going to use the same v value for all of the points As you can see here, all of the m points that were in the original data space are now mapped to this single dimension. In general, this is the idea of a linear projection, where we're taking a point and projecting it into another space. The point can have n dimensions, and what we need to do is select a set of basis vectors that we might have up to capital K vectors to represent the points. Just like we did in the last slide, we used a single vector in 2 dimensions to represent the points in a one-dimensional space. While the example looked at projecting a 2-dimensional space into a one-dimensional space, this is a general problem where we can take a high-dimensional space of any size and project it into a lower-dimensional setting. Here what we want to make sure is that we consider only orthonormal bases, where each basis vector, when multiplied by itself, will have a unit value, and all of the basis vectors chosen are orthogonal to each other. That is, that their product equals 0. We also have to select the center to define the mean of the input data so that we can concentrate on capturing the variance and not the actual values themselves. We're going to get a reconstructed point for each of the points in our input matrix as a dot product between the orthonormal bases vk times the difference between the point and the mean as the coefficient for that particular basis. One way we can achieve this projection is using principal component analysis, where we're doing exactly what we want to do in projecting into a lower dimensional space. For example, projecting natural language data into a 50-dimensional space from the original high dimensionality space where each dimension is one particular vocabulary item. We can also carry it out in this toy example that we've been illustrating of projecting a 2D dataset into a one-dimensional space. The key problem that we want to do is find a projection, perhaps of multiple dimensions, that reconstructs the dataset with minimum reconstruction error. And what we mean by minimum reconstruction error is the ordinary least squares difference between the projected data point and the original over all of the data points in our set. We can think of this as expanding the second term here as this term here, where we're looking at the mean of the data points and their reconstruction times the principal components, 1 through capital K, times the coefficients used to represent that point's projection on that particular orthonormal basis. We need to choose the V that minimizes the residual variance left over that's uncaptured by the reconstruction. For that reason, each of the V's that we choose also has to represent the direction of maximal variance left over in the dataset that's not captured by previously selected dimensions. We can see that at work here. We have a dark gray line that indicates the principal component that's selected, and the red lines indicate the variance that's not captured by the dark gray line. We can see when the dark gray axis is aligned to the pink axes, we have the best representation as the red lines are the shortest. When the red lines are long, this means that the V vector that's chosen, represented by the dark gray line, is suboptimal. Let's take a look at the reconstruction cost J recon. We can see that a point is exactly represented by the case where we have done the decomposition into orthonormal bases, but we use all n components. But in PCA, we only reconstruct with a smaller number of dimensions, capital K. Then we can think of the cost as simply the ordinary least squares difference between the points in their reconstruction, which we can draw out. First, we're going to go through all of the data points, 1 through m, and put the actual value of the point which we can get by using all n components minus its reconstruction by using only the first k. And this is squared loss. We can write this out as this is because we can just clearly subtract this from this and just take the remaining points, which is going to start our index from k plus 1 all the way to n. Expanding the squares, we get something like this. Here we have our cost terms, but because the covariance matrix shows that we have orthonormal bases, so all of this gets zeroed out. And here, this part equals just 1. We've written this out for you on the next slide. What we can do is go back to the idea of the normal distribution or Gaussian and try to apply eigendecomposition of the covariance matrix as we saw in the last section. We're going to write the covariance matrix in terms of eigenvectors. As you can see here, we have the eigenvectors and they're scaled appropriately by the eigenvalues. We can make sense of this on the graphical form here, where we have chosen the eigenvectors to be orthonormal bases that are being scaled by their eigenvalues. So we have the largest eigenvalue here that's representing the first principal component, and the second eigenvalue here representing the second principal component, where the data is centered at its mean, and the ellipse that's defined by the eigenvectors and values confine the data set. This then leads us to the basic PCA algorithm, where we're going to start from our rectangular matrix, center and normalize the data set to ensure that we are capturing only the difference in variance of the different dimensions. We then compute the covariance matrix sigma by taking the average of the square of the centered data matrix. We then need to find a method to calculate the eigenvectors and the eigenvalues of this covariance matrix. Computing the full matrix is quite slow, so we want to find a faster way to compute the k eigenvectors with the highest eigenvalues. One way to do that, as we'll see in the next section, is the idea of singular value decomposition, or S3D.